I'm going to give you a talk today on Vagabond. Vagabond is my new refinement software project that's quite young. But before I begin, I'd like to I have some acknowledgements to make first. Thank you very much, in particular to the authors of three software packages, Coot, RefMac, and PDB Redo, all of whom are here today. I've been able to build upon this work, so it's been really, really fundamental in helping me get off the ground. I'd also like to thank Dave Stewart from Diamond Light Source and Diamond Light Source for financial support for allowing me to actually start this project. And also particular thanks to Arwin Pearson and James Holton for giving me encouragement and support during this project's duration. The one-line summary of Vagabond is that instead of considering the model as a set of atoms, instead we focus on the connectivity between the atoms and produce a model entirely based on the bond network of the protein. And I'll explain what the advantages are in a moment, but first I'll recap how atomistic refinement works during model refinement. So if we have some electron density, we can place atoms at specific x, y, z coordinates in three-dimensional space. And each one of these atom positions actually represents a range of possible atom positions where the atom could be found. And we describe this using a Gaussian distribution, the width of which is denoted by the B factor. And if you happen to have high resolution data, then we may be able to even model an ellipsoidal B factor, which when combined with the positional information requires a total of 9 parameters per atom. And this is also in comparison to the simple case using one B factor, which requires 4 parameters per atom. And in both of these cases, this is a very large number of parameters per atom and almost entirely usually exceeds the number of unique observations during a data collection. And if you didn't add any additional restrictions, then this would be a very unstable refinement and lead to overfitting. So for atomistic refinement, the target function is actually split into 2 components. One half is the agreement between the data and the model, and that drives your model towards the correct solution. But to keep it stable, there's an additional component of restraints which are applied to the model alone, and that includes things such as bond lengths and bond angles, which we know very well and have been empirically derived and are present in the literature. This is all very well, but there are still some problems which have been noted in the literature with this setup. And I will demonstrate this using serine residue. So serine residue with 2 carbons and a terminal oxygen. And in a protein, if that terminal oxygen were to be more flexible than the 2 carbons, then this will generally be propagated in the protein by a twist around the carbon-carbon bond, so that torsion angle can occupy several values and produce a range of possible oxygen atom positions. And if we have a look at the distribution of those positions, then it is very much like a banana and not very much like a lemon, which is accessible through B factors. And to show you the long range effects of this, if we have a terminal bond here, I've displayed the carbon-oxygen bond of serine and the range of possible oxygen atom positions. Here's the banana. Now, the more spread out the atoms become, the curvier the banana becomes. And as the banana becomes more curvy, the center of mass of the banana starts to fall off the surface of the banana. And this means if we're modeling this with an atomistic distribution, then we have to place the atom at that mean position because the B factor is symmetrical, which means that there's going to be a systematic bond shortening, and this systematic bond shortening is going to fight against the model restraints. And this seems unreasonable because torsion angle should be able to freely vary, so it shouldn't be fighting against anything that we put into the model. So This is only a single bond, but it actually has a significant effects. So for example, if we consider a lysine side chain, which is longer, then each one of these bonds is going to inherit the distribution of the previous bond and add to it. So your bananas get larger and more complex. And when you consider, especially in a low resolution structure, that the backbone might have an interesting distribution, then you rapidly end up with a fruit salad. So how does Vagabond deal with this? So the Vagabond uses the Bondbased network in order to create the model. So an internal coordinate system has been used before, for example, for molecular dynamic simulations, for macromolecular crystallography, and the basis is the same. The internal bond coordinate system consists of bond lengths, angles, and torsion angles. In my case, for bond lengths, I keep all of them completely fixed, and for the vast majority of bond angles, I keep them completely fixed as well. But a very small number of them are allowed to vary freely. And for torsion angles, if they can vary, they are also allowed to vary freely. So the result of this is that I only have constraints in my model. I don't actually have any restraints as it stands. When you parameterize with a bond-based system, and I'll go into the details of that in a moment, I end up with about a 60% reduction in parameters for modeling a protein. Right, so what you do then is you take an atom. So one of the atoms in the structure does actually have a defined position in the unit cell. So every polypeptide chain has an anchor atom. And from this, the rest of the structure will be defined. In the original atomistic model, this would have been associated with a B factor, but I don't use B factors. I replace this with a list of explicit atom positions. And then you can use the bond length and angle and torsion angle information to recursively tie up the rest of the structure. Now, this completely accounts for the positional information of the protein, but what about the flexibility? Well, then we go and think about the list of explicit atom positions, and we take each sister position, and we can define a relationship between the sister position and the average atom position for that atom. And we can use that relationship to define a deviation in the torsion angle, which is then propagated to either the N terminus or the C terminus. So the result of this, if I show you the result, this is a screenshot from the Vagabond GUI. Here's an arginine sidechain which has been refined. And as you can see, the two nitrogen atoms look incredibly close together. They are actually that close together, and it looks ridiculous. But this is actually the average atom position. And this arginine actually represents a set of 120 different arginine conformations, each of which does have perfect bond length and angle geometry. And as you can see, this is a perfectly valid scenario, but the average position does look very weird. So what's the target function for Vagabond? Well, Vagabond works in real space. I'm going to use Serine to demonstrate this. So imagine that we have some observed weighted electron density here with a disordered terminal oxygen. And say we have a model which we're trying to fit, and our model is very simple and doesn't contain any flexibility in that oxygen atom. So if you now calculate the density from that model, then that is not going to fit the weighted density very well. So if we have a look at the correlation coefficient, then if we're comparing the weighted density voxels against the calculated density voxels, then this is going to have a okay but not great correlation coefficient. If we then go back to our model and we try various things out, and one of the things that we might do is to introduce some variability in that terminal oxygen atom position, then when we calculate our electron density, then we're going to better fit that disordered oxygen atom position, which means that when we have a look at the correlation graph, we go from an OK density to a stricter, better correlation coefficient, and this will be a good step, so we keep that step and then we move on to the next stage of refinement. So that's what happens on a local level. the global protocol for refinement is that I always take the end result from existing software package which refines to completion. So you take that file and you input the atom positions, the sequence, the connectivity in order to tie up your protein, and then we can choose an anchor atom and we'll tie up the protein from there. So what you can see is that because the bond lengths and angles are fixed to an exact value, that value is actually the empirically derived values in the literature, and this means that there's this error that gets introduced at every step, and then as you go along the chain goes off course, which isn't very helpful, so we need to adjust the torsion angles and the parameters that we can use in order to bring that back onto the original path from the PDB file. And once we've done that, then we've used the initial PDB positions, and we're not going to worry about them anymore, so we can discard them, and from now on, we will just focus on fitting to the electron density. And when we fit to the electron density, we want to worry very much about the flexibility, and so we worry also about the ensemble of the proteins that we're dealing with, and we can introduce, firstly, global whole molecule rotations, such as rotations and translations, which are going to soak up the variability in the electron density. And we're also able to introduce intramolecular motion along the backbone and also along the side chains in order to further account for the variation in the electron density between our observed electron density and our model. So, the one thing I wanted to do was make sure that it worked across a range of structures. So I took a sample of about 1,000 almost randomly picked PDBs from the PDB, and then I'm going to show you the results from PDB redo so I could take the best refinement for that. So I'm going to show you the graph of, this is the original R factors along the x-axis, and the number of R factors, number of PDBs with that R factor along the side, and this is split into R work and R free distributions. Now, this is the original work, and Vagabond has not yet achieved the same R work and R free values. It's a young project, and I'm still not fully fitting my model. However, the Vagabond results are like this. So the gap between R work and R free has significantly reduced by about a half, and that's also in cases where the R work and R free roughly agree with the original value as well. In fact, it's even a smaller gap at that point. And currently, my average R work and R free values are roughly 25–27%, and in order to match, it would need to go down by about 5%. However, despite that, the reduction in the gap between R work and R free does have a serious impact on the electron density. So I'm going to show you an example from the PDB. This is one that I randomly came across, 20N8. I know that I'm part of a low resolution discussion section, but if I'm going to try and show you something with fuzzy maps, then it's not going to be particularly convincing. So this example is 1.35 angstrom resolution. And I'm going to, this is also the average atom position from Vagabond, and it's actually representing a set of 120 individual structures which account for the flexibility of the molecule. And I'm going to focus on one loop region, and I'm going to show you various electron density maps now. So the first electron density map I'll show you is from Atomistic refinement, essentially almost identical to the version from the PDB redo. So this is a loop region involving a lysine. And as you can see, the backbone density is not connected very well in this region. And so I'm going to refer to this model now as the uncorrected model. And I'm going to show you what happens when you pass the uncorrected model through Vagabond. And now if we have a look at the electron density for this region, the backbone density has reconnected, but it's no longer going along the original path of the model. So it's possible to correct this model to a slightly more corrected model, like so. And what's happened here is that lysine has switched from one minimum in the Ramachandran plot to a different valid minimum in the Ramachandran plot. And I'm going to show you now some numerical analysis of the various maps and models that you can create. So what I'm going to do is show you a correlation coefficient of that little backbone region there in real space. And we're going to compare the two models, uncorrected and corrected. And we're going to compare them to maps from the refinement of either of those models. So we're either going to use a map where the input model is the uncorrected model or the corrected model. And so I'll show you the results for the two kinds of refinement programs. So firstly, with an atomistic refinement program, if we use a map using the corrected model as an input, then when we compare the correlation coefficients, as you'd expect, the correlation coefficient goes up as a result of using the corrected model. However, in the reverse scenario, if the input model is incorrect to start with, the uncorrected model actually has the higher correlation coefficient. So it turns out that in this case, the map that has gone into refinement is also the map with which it will correlate, the model with which it will correlate better. So the results for the Vagabond refinement is not the same. So in both cases, the correlation coefficient increases regardless of which map you've used to refine the model against the map. And you can see that this is consistent with the fact that the input model isn't biasing this as much, and it's also consistent with the reduction in the gap between R work and R3 that indicates reduction in the level of overfitting in this scenario. So that's an example where I feel like Vagabond is clearly making this difference in the level of overfitting. So where does Vagabond go from here? Well, along the main path is actually continuing to work on the basic refinement engine, which powers this. Obviously, I need to worry about all of the small cases and so on that have been refined through the last few decades. But also, I am not fully fitting my model to the data yet, so there's still a long way to go. And I'm primarily working on crystallographic data, and hopefully the paper with what I've shown in this talk will be coming soon to a journal near you. And then there are various side projects. So for example, I'd like to have a look at fitting to multiple data sets. This isn't current. There aren't very many options available for doing this at the moment. And sometimes it's the way where people are able to get a foothold on their model, but it's not quite easy enough to do so yet. I'd also like to have a look, because of the model is so different, because it doesn't use B factors, it might be very interesting to apply this to cryo-electron microscopy data. It might be complementary to what's being used at the moment, but I haven't looked down these side routes yet. So the availability of Vagabond. Vagabond is available at this website here. I'm going to display it really large, vagabond.hgin.co.uk. Write that down in your copybooks now. So please visit it. Email me on the email address on the website, should you so wish. And please tell me if you have any problems, if you want your PDB to be refined in Vagabond and you want to make sure it's working and so on, please do try. You can install it freely. It's open source and free software. So thank you very much.
Thank you, Helen. That was great. Questions? I have lots of questions, but any from the floor? So one Hello.
Oh, sorry. Where am I looking?
Okay, it is Gerard.
Hello.
Yes, well done for getting back to first principles in refinement. Just for the record of history, some of you, maybe very few of you, may remember that the first refinement program for proteins was Bob Diamond's real space refinement program,
Yes.
published in 1971, which economized on parameters using exactly that idea. Because at the time, you had to do refinements on machines that had a small fraction of a megabyte of main memory. So well done for taking this up again. The problem with torsion parameterizations is that the sort of nested torsion angles can produce movements or dependencies of the movements of large pieces of structure on each of the most internal torsion angles. And that gives sort of stability problems in the optimization.
Yes.
So Bob used only a 10 residue molten zone, which of course can correct only local problems. But I'm sure that nowadays with the optimizers we have, much more can be done. So
Yes.
Good luck.
Thank you.
Yeah, thank you, Helen. It was really great talk. I have one question. You mentioned an anchor atom.
Yes.
How would you choose this anchor atom?
Right, so the actual identity of the anchor atom doesn't matter too much because I don't have any dependence. The flexibility isn't dependent on where the atom is, and the positions aren't strongly affected either. But I generally choose the nitrogen closest to the center of the protein. Center of mass.
The only question I was going to ask, how do you record your results? You know, do you record the multiple solutions that you've got, or do you take the average of, you know, NE2 for the arginine? Or what?
Yes, so there are a range of output files. There's a file that's a bespoke file format which you can use to load back into Vagabond should you want to continue with a given model. There's also an average output position for a PDB file where the B factors try to represent the anisotropic B factor tries to represent the range of possible atom positions. And then there's an ensemble PDB file that's enormous that's written out, and that allows you to see where all of the atom positions are in COOT. And then there's viewing the ensemble in the GUI, which is a separate way of seeing the range of states.
Presumably where the B value becomes very high in your average model, that's the interesting places to look at.
Yes,
Yes.
yeah. Thank you.
So just one thing I noticed looking at the your ensemble bundles, how do you decide the kind of global scaling that you apply? Because it looked just from a quick view that perhaps if you had a kind of underlying B factor, that could shrink your bouquet of ensembles, and that might also help minimize the number of parameters you're trying to fit.
Yes, I agree that, so I have the option to include a global B factor. Generally, I haven't seen this to have improved any structures in any way. As I've been ironing out bugs, that has stopped being useful for me. So at the moment, it seems to be behaving best without any introduction of a global B factor. I imagine that's an interplay between the way that the torsion angles are allowed to vary versus a kind of static motion of the entire protein. And I've generally found that not applying a global B factor has used to help when there were bugs, but no, it doesn't help anymore.
Yeah. It might help for visualization, that it simplifies the structures. As well.
Yes.
Right, I think we should thank Helen once more.